Let's talk about how you write a power series from a function. Now, one thing that happens is that we can operate or work on power series. So let's start out with that. Let's do operations on power series. Since power series are just big addition problems, we can add them together, we can subtract them, we can multiply them, we can divide them. We can also differentiate, so you can take d dx of a power series, okay? You can also integrate a power series. So we've got all those options open to us. When we do work on power series and try to create power series, a lot of times we use a basic idea of the geometric series. Remember, the geometric series looks like this: n equals 0 to infinity, ar to the n. This converges, so it converges if the absolute value of r is less than 1. Not only that, this has a sum. The sum is a over 1 minus r. So we use that quite often when we're trying to create power series. Something else that you might recall is that when you have a power series with an x, that's what power series have, they've got a variable x, that you sometimes have a center. So if you've got x minus c, then the center is c. Now this is just part of the power series, but when you've got that, you've got a center. So let's use these ideas and come up with a few examples. First thing I want to look at is a power series for 1 over 1 plus x. Now that's a function that we can use. So the function f of x is 1 over 1 plus x. If you notice, it looks a whole lot like the sum of a geometric series. In fact, let me build it so that it is. I'm going to write that as 1 over 1 minus a negative x, okay? So now it's got 1 here, which is a big deal. It's got a minus here. It's got a constant in the numerator, and it's got our x value, or our equivalent to our r value. Well, if you kind of back up on this geometric series, you'll notice that that stands for the series, or this is the sum of the series, n equals 0 to infinity of ar to the n. Here's a, so that's 1. R is negative x to the n. So ar to the n, this is n equals 0 to infinity. 1 times something, we don't need that. This is minus 1 times x, so I'm going to call this minus 1 to the n, x to the n. So now we have a power series for the function 1 over 1 plus x. Let's look at a power series for 1 over 1 minus x. So g of x is 1 over 1 minus x. Well, that one's actually easier because that's already written as a over 1 minus r. So that one has the sum, n equals 0 to infinity, of a, here's the a value, r, okay, here's r, so x to the n. So this series is n equals 0 to infinity of x to the n. Now, what if you added them together? Okay, so let's say we have 1 over 1 plus x plus 1 over 1 minus x. Well, fractions can be added if we get a common denominator. So I will multiply top and bottom by 1 minus x. So I'll have 1 minus x squared. I'm just going to skip the algebra a little bit. Plus, this one's got to be multiplied top and bottom by 1 plus x. So I'll have 1 plus x over 1 minus x squared. If I add those two, I've got 1 plus 1, that is 2, minus x plus positive x is 0. So I've got 2 over 1 minus x squared. Now I added the two functions together. This is my function f and this is my function g. So this is f plus g. Operations on power series tell us that we can add the series together. So the series for this one was right here. It was, and I'm going to make this just one series. So n equals 0 to infinity. I've got minus 1 to the n, x to the n, and then I need to add to it the series for the other one, which is x to the n. So there is the sum of those. Now, it doesn't look very good. What you could do is you could factor out the x to the n. And here's what you would have. You would have n equals 0 to infinity. If I factor out the x to the n, I usually factor it on the other side, but that's okay. We'd have minus 1 to the n plus 1 to the n. Okay? Now, you can't really put those together in a great way, so you'd have to do some other work to try to make it look a little bit different. But we just added two series together. And what we got was we got the power series for 2 over 1 minus x squared. Now let me show you another power series for 2 over 1 minus x squared, because this guy right here is built just like a geometric series also. Okay, so another look at this. And you can test this out algebraically and see if this matches. But if we've got 2 over 1 minus x squared, then this is a, this is 1 minus, this is r. Okay, so the series for this, very easily put together using the geometric series model, is n equals 0 to infinity, a, and then r, which 1 minus, so we don't take the minus with us, so we've got x squared to the n. So what we end up with is this series, n equals 0 to infinity, 2 x to the 2n. Now, if you wanted to, you could validate the fact that this and this are the same. But we have a series for this. All right, now let's find the interval of convergence. Might as well do that. Okay, what we've got to make sure of, this is a geometric series, so it's kind of cut and dried on this, but we have to have r, which is x squared. So the absolute value of x squared is just x squared, and it's got to be less than 1. So that gives me minus 1 is less than x squared is less than positive 1. Well, looking at that, it's a little ridiculous to say x squared is minus 1. We don't do that. So in reality, we go 0 is less than x squared is less than 1. Now, if x squared is between 0 and 1, then x is also between 0 and 1. X could also be negative. So we'd have x is a value between actually 0 and 1 or minus 1 and 0. So x is between minus 1 and positive 1 to square it out to make it between 0 and 1. Now, if we check the endpoints, let's look at the endpoints. If you look at the endpoints, you've got plus 1, you've got minus 1. Take a look at the original function. Is that defined at plus 1, at x equals plus 1 or x equals minus 1? No. So we will not consider those endpoints because the function's not even defined there. All right? Let's take another look at another function. And the next one that I want to look at is this one. This one is the function, I'm going to call it h of x, is equal to 2 over 6 minus x. And I want to center this one at -2. So let's figure out what h of x needs. Well, let's write it like a geometric series. So the first step, so step 1 is we've got to deal with the center. All right, so step 1, we've got to deal with the center. So we've got 2 over 6 minus, and then we've got to take x minus 2. So x plus 2. Well, that's not equal to the original problem, so I've got to make it. What I did was I subtracted 2, so here I've got to add 2. All right, so now I've got this. I've got 2 over, now 6 plus 2 is 8, minus x plus 2. This is centered at -2, so that's step 1. Step 2 is to make the constant in the denominator 1. So turn the constant in the denominator equal to 1. You do that by dividing. So I need to divide everything in this entire fraction by 8. So to do that, I take 2 divided by 8. I take 8 divided by 8 minus x plus 2 divided by 8. That gives me 1/4 over 1 minus x plus 2 over 8. So this now is a, this is r, and so we've got a over 1 minus r. So what's my series? Here's the series. Series n goes from 0 to infinity. A is 1/4. 1 minus r, here's r, so we've got x minus 2 over 8, x plus 2 over 8 to the nth power. So there's a series for this function centered at -2. Let's try another one and see what we can come up with. The next one we're going to work on is arctangent. All right, so find a series for arctan x. So I'm going to call this function capital F of x. All right, it's arctan x. Now, arctan x is not written as a over 1 minus r. But the derivative of arctan sort of is. Remember, f prime of x, if f of x is arctan, f prime of x is 1 over 1 plus x squared. Okay? So the derivative of arctan is like this. Well, that is a over 1 minus r. The series for the derivative is n equals 0 to infinity, 1 times r. Now this is minus, so I've got to go minus x squared to the n. What I've got is something I've got to work a little deeper on. This is equal to the series n equals 0 to infinity. We've got minus 1 to the n, so this is an alternating series, and then x to the 2n. So there's a series for this. Now, how do you get from this to arctan? Well, you have to integrate. So let's integrate the series. So let's integrate the series. Now, it's just a big addition problem, so we can integrate each part. So here's what I'm going to do. I'm going to write the series notation here, and then I'm going to put the integral, okay? The minus 1 to the n, it's not going to really relate because we're integrating with respect to x. So I'm going to integrate here. I've got x to the 2n dx. So now, if I integrate, I'm going to get the series n equals 0 to infinity minus 1 to the n, and then I've got to use the reverse power rule. X to the 2n plus 1 over 2n plus 1. Normally plus c, we usually don't deal with that much here. And there is a series for arctan of x. So we took arctan, we made it into something that resembled the result of the geometric series. We wrote the geometric series for it, went back and integrated. Now, if you want to see where it's defined, you'd have to check the endpoints and all that sort of thing, but that is a little bit of work with operations of power series.